Hello, my name is Ken. I'm with Foxx Pedals. Today we're going to be looking at sound. I have here on the oscilloscope a sine wave. The sine wave is being generated by a function generator. And I have it set to a frequency of about 440 Hertz, which is the note A. If we turn up a speaker here a little bit, we can hear what that A sounds like. It's kind of a pleasant tone. It's not too sharp, not too bright. But if we change it, this is what a sine wave sounds like. If we change it to a triangle wave, you can hear that it's a sharper tone. Back to a sine wave, back to a triangle wave. So if we look at the waveforms, we can see that a sine wave has a nice gentle rollover at the top. It still falls at about the same rate as the triangle wave, but it's got a gentle roll and then comes back up, whereas the triangle wave has very sharp transitions at the bottom and at the top. So it hits very quick, goes back down. Also notice that it doesn't spend very much time at the highs or at the lows. So there's the difference between a sine wave and a triangle wave. There's a little difference, but not a whole lot. Now, if we were to turn that waveform into a square wave, it would make quite a bit of difference. Let's take a look at a square wave. The first thing you notice is how much louder it is. I'm going to turn the volume down on the speaker a little bit. You'll notice that the square wave spends a lot of time at the high and a lot of time at the low, and has a very fast transition between high and low. It's a little bit more sharp. That's because of the very sharp transitions. You get a sharper tone, and then it has more volume because of the amount of time that it's spending at the extremes. If the wave were to be right here in the middle, you'd hear no sound. You don't hear the sound until it gets either very positive or very negative as it drives the speaker. So let's go back to the sine wave, and you can hear the difference in volume again now here. The volume here almost went away as we got to the sine wave, so I'll turn it back up a little bit. Alright, now I'm going to change the frequency. Like I said, this is 440 Hertz. If I change the frequency to double it, well, it'll go from 440 up to about 880. You notice that is about an octave higher. So if I go from 880 back to 440, you can notice the difference there. Here you can see in our frequency right here we're about 440 Hertz. Here we go up to about 880. Again, you can hear the difference there between the two. Now what if we were to half it? If we go from 440 down to 220. You notice 220 is an octave lower. So as we half the frequency, we go down an octave. So each time we double it, we go up an octave, double it again, go up another octave. So you can see the relationship between the frequency and the pitch that you hear. Now, let's try something. If I can go from A here up to a higher A, all the notes between those two A's should be able to be represented here on the oscilloscope and with the function generator as well. If I start at 440, I can go up from an A to a B, C, D, E, F, a G sharp, and then an A. That's kind of the whole octave there. You can get all the notes just by changing the frequency. The other thing we can do on the frequency is change the amplitude. And you can see here, if I change the amplitude, I can turn it down, turn it back up. You notice the main difference there as I change the amplitude is that the volume gets softer and louder. Like I said, if I were to have the amplitude completely in the middle here, you can see I can't turn it all the way down, but you can see it almost goes away When the amplitude gets down there, when it gets back up, you can hear it. Now I'm using about a 2-volt peak-to-peak signal here, and I'm just driving it into a set of speakers so that you can hear what the sound sounds like here. So that's the end of the quick look at sound. You know, the fundamentals of changing the frequency and changing the amplitude, and then the types of waves. We've looked at both the sine wave and the triangle wave, and we've looked at a square wave.